Good morning, good afternoon, good evening. My name is John Kingham, and I am the host for today's webinar. Derek Prinsloo will be presenting. Derek is one of my go-to presenters. He has worked at several different service positions within Bentley, Nevada, which gives him a well-rounded and complete perspective. Derek has been working as an ASA for the past decade or so. We will be recording today's session, and in an effort to make these videos available to you and your colleagues at a later date, we ask that you make sure that you are on mute and refrain from broadcasting your video. If you have called in through a phone, please hit *6 to mute and unmute. I've been working with the service organization, and we're going to add 5 more webinars to our series starting the week of 13 July. When I get a synopsis of those webinars, I will be sending out a continuation email to all who have registered for these webinars, letting you know when and what topics are going to be covered. After today's session, I will also be sending you a little thank you email with a survey enclosed. Please, please, please take the minute or two to fill that survey out. One of the questions I ask is, what other topics would you like to see? So, and I am using that data to help drive some more webinars. So today we will be using the Slido app for questions. As a default, your questions are made anonymously, but if you prefer, you can put your name in as well. I also always recommend voting on your own question. It gives it extra priority, and you can vote on other people's questions if those questions are pertinent to your needs. And as we are recording the webinar, we will wait until the end. We'll stop the recording, then we will pose and answer those questions. So without any further ado, let me turn it over to Derek.
Thank you, John. And welcome, everyone. Thank you for joining us for an overview of vibration plot formats. As John mentioned, we're using the Slido app for questions, and the code to get in is Bentley Plots. As I go through the presentation, in the top right-hand corner, I'll have the same code listed up there in case you happen to forget what it is. But before we dive into things, I wanted to mention one topic here. Training has always been a high priority for Bentley, Nevada, and historically we've always done that training in person. We can either bring customers to our training centers like Houston or Minden or other places around the world, or we even go to customers and bring the training to them. In the strange new times, we've pivoted somewhat, and we are now also offering remote learning courses. So our courses that you may recognize, things like 3500 operation and maintenance, fundamentals of vibration, machinery diagnostics, recip compressors. These are all courses that we're offering now remotely, and we're utilizing the latest in technology, things like cameras to view the rotor kits and see the balance weights being put on, remote desktop type applications, so you actually can do the clicks in System 1 or Adre or other software yourself, and other collaborative type apps that allow students to break out into smaller groups, work on assignments together, that sort of thing. I'll admit that remote learning does not replace that camaraderie, that collaboration that in-person training has, but we've done our best to replicate that as much as possible, and we think this still provides a lot of value for you. If this happens to be of interest for you, go to bentleytraining.com. If you just go to that website, a big pop-up shows up, or if you go to bentleytraining.com/remote learning, you'll have all this information. You'll have the dates and times when these are going to be available. Please check them out. I will also mention that the information that we'll be going through today is a brief synopsis of one part of the Machinery Diagnostics course. I like to describe today's webinar as the what. I'll be describing what the different plot types are and what you use them for. But if you really want to understand why the data looks the way it does in those various plot types and when to use those plot types more in depth, the Machinery Diagnostic course gives you all that information. So please definitely go check that out if today's topic is of interest to you. So to set the stage for our session today, I want to make sure that we differentiate two different types of plot formats: steady state and transient. And when I say these two different types of plot formats, I'm talking about the speed of the machine. So for steady state, we're talking about where the machine speed is relatively constant. So that's not to say that process conditions are constant. You know, processes can still change depending on what type of machine you're looking at. But relatively speaking, the machine speed should be relatively constant for it to be considered steady state. In contrast to that, excuse me, is the transient plot format. In this case, when we say transient, we're talking about a change in RPM. Things like startup, where the machine starts up from either stopped or from slow roll; shutdown, where the machine shuts down from steady state conditions back down; or even overspeed, where the machine goes beyond the typical running speed of the machine. In either or all of these scenarios, how the machine responds as it changes in speed tells you a lot about the condition of that machine, tells you a lot about the characteristics of that machine. And the plot types that we'll be looking at that are more specific to transient data, that is change in RPM data, will highlight a lot of those characteristics and features. I will mention here that the steady state and transient terminology is somewhat of a Bentley specific terminology. A lot of customers, transient more refers to, you know, events that are short in duration, you know, bump in the night type events. But for us, when we say transient, we're talking about delta RPM or change in RPM. And another thing I want to highlight when we're looking at plot formats is the differences in types of data. So specifically, I'm talking about static data versus dynamic. And when I say static data, I'm referring to graphic formats that use scalar values. So overall values. If we were to use vibration as an example, overall vibration amplitude, or filtered 1x amplitude, or filtered 1x phase, or bias voltage, or gap voltage. These are all scalar values that can be plotted over time. Typically speaking, trend plots or static data is sampled in the order of, you know, seconds or minutes or hours, and they can be put together on things like trend plots and other types of plots. On the other side, we have dynamic data, and this is what we refer to as waveform data. So dynamic data represents as best we can, the true nature of that waveform. So the sampling in this case is in the order of milliseconds rather than seconds or minutes or hours. And we can take that waveform data and we can transform it into things like spectrums, but those would be what we call dynamic data. So as we go through looking at the different plot types, in the top left corner, I'll have an orbit that's colored to either tell us whether it's a steady state or transient type plot format. And I'll have these symbols that tell us whether it's static data or dynamic data in that plot format. But now that the stage is set, let's actually get into the different types of plots. First, I wanted to discuss one that is we call a tabular list. While I wouldn't say this is strictly a graphical plot format, it is still a presentation of digital data in a logical grouping of sorts. So the first way we can display a tabular list is sorting the data by channel. So if we look at the header up here, we'll see that the data we're looking at is for one particular channel here. In this case, it's BB1X. It's mounted on the turbine. It is mounted in the 45 degrees in the right-hand direction, and the units are listed up here. But in the table itself, you'll notice that all the values that we're seeing here are for that one channel, but they are listed over time. So each sample that's been collected here is listed as a separate line item. And as we go to the right in the table, we can see the speed associated with each of those samples. We can see the direct amplitude associated with each of those samples, and also the average gap. In the configuration, you can choose whatever variables you want to show in this table. You could show 1x amplitude and phase, 2x, et cetera, But in this case here, the key for differentiation here is by channel, shows all of the samples for that one particular channel. The other type of tabular list that we can show is by sample. And in this case here, generally you would use this when you've got more than one channel that you want to compare to each other. So in this case here, we've got BB1X and 1Y and BB2X and 2Y. In the header, you can again see how they're mounted. So 1X and 1Y are obviously 90 degrees from each other. They're mounted 45 degrees right and left. And same for 2X and 2Y. And we can still see the units for each of those. But in the actual table itself, you can see that now instead of showing all the samples together, you're showing one particular sample for all 4 of these channels. So here, this sample was taken at 6:45 in the evening and at 3598 RPM. And now we can compare the vibration levels for each of these. You can see compare the vibration, the average gap, the 1X amplitude, and the 1X phase. This type of table I find is typically used if you're doing maybe just a quick summary report, if you want to just get a snapshot of where that machine is at a certain point in time. The by sample graphical or tabular list is useful for that. You can copy and paste it, throw it in a report, and you've got a nice quick summary of where everything is. The next type of plot format we're looking at is, again, typically going to be for most useful in steady state plots. And this is using static data, and that is our trend plot. This is likely going to be the most popular plot that, or most commonly used plot in industry. And it is in the Cartesian format. On the x-axis, you've got time, and on the y-axis, you've got amplitude. And as data is recorded, it is plotted on that X versus Y plot. The trend plot is very useful for just seeing the general shape of data or behavior of data, but also it's incredibly useful for correlating data. So being able to see how different vibration channels respond to each other. If one goes into alarm, did the other channel also react, whether it be X versus Y or inboard versus outboard channels. Plot them on a trend plot, and it's easier to see how they react to each other. But you can also then correlate other variables, whether it be flow, load, pressure, temperature, etc. Being able to plot all of these together, synchronize the cursors and see, okay, if vibration shifted here, vibration went up and then went back down. Okay, what did my pressure do? Did pressure change at that point? Maybe the load changed or the temperature change. Understanding how things react to each other helps a lot with just general condition monitoring and also diagnostics. Another thing that the trend plot allows us to do is easily visualize alarm levels. For Bentley Nevada racks, things like the racks like the 3500, we often set alert and danger set points for the channels in those racks. And in our software, like System 1, those alert and danger set points are automatically imported and displayed on the trend plots. So here you can see how close these trends are getting to these alert and danger set points. In our software, we also allow the ability to add additional software alarms. So for this scenario, maybe we would add a software alarm at 3 mils peak to peak. And this would tell us every time this trend bumps up into that 3 mils range, and that might tell us something significant about the operating condition of that machine. Other items to note here for trend plots, which are, again, you're going to see similar sorts of things for the other plots, is information on the axes. So on the horizontal side, on the X side, it tells us that this is time, and each of these divisions is 2 hours per division. That /div is per division. So here we can see from 11, this is 13, 15, 17, 19. So every one of these divisions is 2 hours. And on the vertical axis, it shows us the scale here. So 0.2 mils per division. So 2, 4, 6, 8, 1, and so on and so forth. Next, we have orbit and time-based plots. For those of you that maybe participated in our Introduction to Vibration webinar a couple of weeks ago, these plots, or at least the waveform plots, should be somewhat familiar. If you're interested in learning more about how these waveforms are derived, please go check out that webinar. But today we're going to talk about combining those and what sort of characteristics we can get from the plots themselves. So the orbit time-based plot combines 2 basic types of plots together, as the name implies. So we've got the time base on the right-hand side here, and we'll see how they combine to create the orbit. But there are a couple of prerequisites to get a good orbit time-based plot. First, you need two proximity probes at 90 degrees from each other. So graphically in the orbit plot here, the probe orientations are denoted by the little black squares in the corners. In this case, the probes you can see from the header are mounted at 45 degrees left and right. If they were mounted at 0 and 90, you would see those squares at 0 and 90 degrees instead. I've just highlighted them by adding these blue lines to show where they're mounted. So you need two orthogonal probes, and you need a key phaser. So the key phaser gives a reference for the once per turn event. So in this case, we can see here from these waveforms, this is 1, 2, 3, 4 rotations that are shown on this particular plot, as we see 4 key phaser events going on here. So when you combine the two of those together, we can see that this is the waveform for the Y probe, and this is the waveform for the X probe. Just as a refresher, a proximity probe can only see a surface moving closer or farther away from it. It doesn't know what's going on next to it. By combining those two probes at 90 degrees, we can now draw the orbit plot. And the orbit plot is the instantaneous position or the instantaneous movement of the center line of that shaft. If you want to sort of picture that, if you were to think of putting a pencil in the middle of the shaft and holding a piece of paper up to it, whatever shape that pencil would draw on the paper, that is the orbit here. And through the magic of electronics, we're able to superimpose that key phaser on it so we can see how it behaves once per turn here. Another observation about this is that these waveforms are very nice, clean sinusoidal waveforms. That's the first visual hint to us that this is probably a filtered signal. And if we go up to the header here, we can again see that this is for the 1x frequency. This is filtered 1x data. Another thing that tells us that this is 1x data is that the amplitudes are shown on the top here. You're getting amplitude and phase. So when you filter it for one particular frequency, we're able to measure the amplitude, so the peak-to-peak amplitude, and the phase. So remember, if you recall back to our discussion of how phase is calculated, you go from the key phaser to the first positive peak. So up here for the Y probe, that is probably just below 360 degrees. And we can see here that's 312. And for the X probe, we can see from the key phaser to the first positive peak, it's about roughly half a rotation. And we can confirm that up here that this is 177 degrees, just a little bit less than 180. So this is all information that can be gathered from this one particular orbit time-based plot. In the header, you'll also note the time that this particular sample was collected. Again, as I mentioned for waveforms, this is a very high density, very short duration piece of information. So this is over these 4 rotations. This takes just over 60 milliseconds for this one waveform. So this one sample was collected at just before 9 o'clock in the morning on the 15th of May. Orbit plots are very powerful as they combine vibration, amplitude, phase, and frequency, and they also give us useful qualitative properties too. So in addition to all the quantitative information in here, things that can be measured, we can also get a lot of qualitative information from the orbit time base. Down below here, we have a much messier orbit time base plot. Still got the key phaser on it, so it still has that phase reference, but this is the unfiltered vibration. And you can tell that here in the header, it says direct vibration. So that's the overall, the unfiltered vibration. And there's no phase measurement. So we know that this is unfiltered. And as we can see here, the path of that orbit is not nearly as clean as the filtered one. There's noise along here. And generally speaking, this sort of kind of chaotic noise is going to be a result of the shaft surface condition. The messier or the more scratched up your shaft surface is, the messier your direct orbit is going to be. Even to the extreme event that there's like a sharp scratch in the target surface, you might even see things like a little ear poking out here in the direction of each of the X and Y probes. Since a proximity probe only observes the shaft surface, it sees a scratch as something, and it thinks that the shaft is basically jumping out towards it. And that's why you get these spikes at 90 degrees from each other. You'll also see those spikes in the waveform plots as well. So if you want to have some usefulness out of your direct orbit, that's why we recommend having as clean and burnished a shaft as possible. Other things that can be gleaned, qualitative things that can be gleaned from the orbit time-based plots is the general shape of it. Is the unfiltered orbit circular? Are there internal loops? Are there double loops? Or is it squashed? Is it very rounded or very squashed? These are all qualitative things that, you could probably derive mathematically. And if you knew what you're looking for, you would understand that that's, there may be a heavy preload on this particular bearing. But if just looking visually at an orbit, it's very easy to see, okay, is that circular or elliptical? So carrying on from the orbit is the half spectrum. So a half spectrum is a mathematical representation of a single complex waveform. So on the x-axis of a spectrum, we have frequency, and on the y-axis, we have amplitude. And some information that can be gleaned from the spectrum and the header again, you can see the overall amplitude for this particular waveform is there. And if you move the cursor to a particular point on this spectrum, in this case, we've got it on this first big spike there. It's a little tough to see on screen, but you can see the black line and the little dot there. So the cursor is there, and in the bottom right-hand side, you'll see the amplitude and the frequency wherever that cursor happens to be. So in this case, we can see that based on the 10 hertz per division, this is 10, 20, 30, 40, 50, 60. So the spike is happening roughly at 60 hertz. And if we were to follow it across, each of these divisions is 0.05 of a mil. So this would be just below 0.85. And if we look down here, we can confirm that it's 0.836 at 60 hertz for that particular cursor location. Other useful information on a spectrum plot is you can tell what the configuration settings are. So in this case, we know that our full scale is 0 to 250 hertz. So this particular plot has been zoomed a little bit to show only up to 200 hertz. We don't have that extra 50 hertz showing. And we know that this plot was recorded with 800 lines of resolution. So if you take 250 divided by 800, you'll get this 0.31 hertz spectral resolution. So all very useful information depending on what you're looking for. Also up in the header, you'll see the machine speed that the sample was collected at and the date and time that the sample was collected at. So how do we get from a waveform to a spectrum plot? Again, for those that participated in the intro to vibration, this may be a bit of a review, but I'll go through it here as well. So starting here, we have a complex waveform. You can see that this in rough shape, in general terms, there's one overall shape here, but there's other information that makes it a bit messier. So if we were to take that and mathematically break it apart using an FFT, we can now get the individual spectrum or the individual frequencies showing. So the overall shape here, we can see that this is the largest piece. And if we know that this is also one rotation in duration, we know that we got one cycle of vibration for one rotation. So we can call this 1x, the frequency 1x. So the frequency of the vibration is the same as the frequency of the rotation. In this case, here we've got 3 cycles of vibration for every rotation. So we would call that 3x, 6x, 8x, etc. And if we then take the amplitude of each of those filtered frequencies, draw it out, and then plot out that amplitude on the frequency axis. Remember, the waveform is on a time-based axis, and the spectrum is on a frequency axis. So if we plot that out and then remove the intermediate steps, we can now see how the waveform relates to the spectrum. So that's how we transform the waveform to a spectrum. And if a half spectrum is a mathematical representation of a single waveform, a full spectrum is a mathematical representation of 2 waveforms in the shape of an orbit. So if we were to convert an orbit into spectrum format, it would be a full spectrum. Again, it requires a pair of XY probes. So in this case, again, they're mounted 45 degrees left and right. And it shows the forward and reverse processing components of that frequency. And we'll talk about what that means in a moment. One thing I wanted to highlight, I forgot to mention it in the half spectrum, is that the x-axis here, we can show it in a variety of different units. In this particular case, we're showing it in the units of hertz. We can also show spectral plots, both full and half spectrum plots, in CPM units, that's cycles per minute. That makes it really easy to correlate to the rotation, the RPM, the rotations per minute. And if you've got a key phaser and on the machine, the software can actually do that correlation for you. And then we can display these units in orders or, NX values. So if you compare CPM to RPM and they're the same, then that's 1x. So we can show the x-axis here in 1x, 2x, 3x, and multiples thereof. Depending on what you're looking at, gives you the information that you need. So how does a full spectrum relate to the orbit? So if we take an orbit and we break it down into a variety of vectors here, we can see the forward and reverse processing values. And in the long axis of the orbit, those two vectors add up to each other. And in the short axis of the orbit, those two vectors subtract from each other. Now I've got a bit of an animation here to illustrate this. So in this case, this is really slow. Let me speed it up just a bit. We've got a single forward processing 1x vector. So this gives us a perfectly round orbit. If we were to add a little bit of reverse processing, you can see how these two, in the long axis, they add up. The short axis, they subtract. Long axis add up, short axis subtract. So this shows us how we get, and this would be an example of a filtered orbit. So this is only showing the 1x frequency. So this is how, and if we bring that 1x up so they're more equivalent, you can see that how in the full spectrum, if the forward and reverse components are more similar to each other, it's going to indicate that we've got a more squashed orbit. If there's more difference from each other, it's going to be a more circular orbit. If we take all of the frequencies into account, we can see how different orbits may be represented. So you might get something messy like a figure 8 like this. And now this is just made up of 1x and 2x components in the forward and reverse procession. So you can see how things like this might show up, or even something squashed, more like a jelly bean type shape. These are all orbits that may be possible through things like rubs, through preloads, through resonances. There are various conditions that may affect the shape of your orbit, and how we represent that orbit in a spectral frequency or in a spectral domain is how they show up in the full spectrum. So moving on here, so we see again the forward and reverse components. If we were to see a full spectrum plot looking like this, where the two peaks are fairly close to each other, we would know that this is likely going to show us a pretty squashed orbit. If we see two peaks that are quite different from each other, we know that we can expect to see a more circular orbit in that type of scenario. So as a reminder or as a refresher, a half spectrum just shows you is a representation of a single waveform. A full spectrum is a representation of an orbit. So a single spectrum, an individual spectrum, tells you what the machine is doing at that particular moment in time. But, as we all know, machines don't stay constant over time. They change, conditions change. And being able to see that over time is very useful. And that's why we're able to lay out our spectrum plots over time now. And this is called a waterfall plot. So the X and the Y axes are still the same as the spectrum. So we still got frequency on the X axis and amplitude on the Y, but now we have a third axis or time. So we lay out each of these spectrums for each time sample that's been collected. Another thing to note here is that on the right-hand side, we do still include the label, the speed label or the RPM label for what speed that particular sample was collected at. And so we can see how these things behave. So in this case here, if we look at the axis here, at about 7 kilohertz, we've got a pretty good frequency showing up here, pretty good signal showing up here. And then at about 3:07 in the afternoon, that signal drops out for some reason, even though the speed didn't really change notably. Likewise, this 3.5 kilohertz looks like it reduces quite a bit. And, there might be other stuff happening down here in the lower frequencies. But by being able to lay out a series of spectrums over time, we can see some useful information for them. And again, this is a waterfall plot. So while this is generally speaking a steady state plot format, because we're relating them to time, we can represent data during a machine startup or shutdown. In this case here, this is a shutdown. The machine was operating steadily, and then it suddenly started to shut down. And we can see that from the RPM labels on the right-hand side. So we've still got the frequency, amplitude, and time. But in this case, we notice that there's a change in speed. So because machines don't shut down in a very linear fashion, or the speed doesn't reduce in a linear fashion, you kind of get this swooping behavior here as the machine-related frequencies change. One item to observe here is that just before the shutdown, it looks like this, what is this, 40 hertz frequency suddenly spiked up really high here. And if we look, we only see it in the forward direction, but not in the reverse direction. So if I were in a classroom environment, I could ask folks, what shape of orbit would you expect to see there? But I'll answer it for you, that if it's all forward and almost no reverse, this would be a very circular orbit. So it seems like something went big down here. But then as you go farther down there, as the forward and reverse are more similar, you'll likely see a more squashed orbit at these lower speeds. Another example here, again, this is a waterfall plot. So over time, we're seeing the samples over time, but still capturing data during a shutdown. We can see the machine frequencies are correlating to the speed of the machine. So as the speed goes down, the frequencies go down. But we see one frequency that remains constant here. And if we put the cursor there, we can see that this is at 60 hertz. And that tells us that even though the machine is shutting down, we got this constant frequency here. This is probably some sort of electrical noise. This was data captured in North America. If you were to capture this data in Europe or elsewhere, you might see that as a 50 hertz noise if you have electrical noise. But for us, we saw that as 60 hertz. So if a waterfall plot is a series of spectrums over time, a cascade plot is a series of spectrums, but now over speed, plotted relative to speed. So on the X and the Y axis, we still have frequency and amplitude, but now on the Z axis, we've got speed. So it'll be listed in the top in the cascade plot. In this case, it tells us that this was captured during a shutdown. So this machine started at 3,600 RPM, and as it shut down, we recorded a series of spectrums over that shutdown. This helps us to be able to see what's related to or independent of speed. Another item that you'll notice on the cascade plot is you'll see the labels here, the 1x, the 2x, and the 3x, and so on. So by correlating the spectrums to speed, we can now draw a nice straight diagonal line through each of those multiples of running speed. So here we can very clearly see that the dominant frequency here is 1x. So as the speed goes up, that frequency goes up. There's some response in the 2x and some in the 3x, but it becomes very easy to see what is related to speed, what frequencies are related to speed here. In this scenario here, we can also see a full spectrum in a cascade plot. So again, we've got the frequency and amplitude, but again, now it's over speed. And this shows us that, if you're to take an orbit plot and press the arrow key and kind of cycle through with the startup or shutdown, you would see how the orbit shape changes. But by looking at a full spectrum plot, we can get some sort of an idea here as well. So at full speed, or at running speed, it's predominantly forward processing, so you're going to get a fairly circular orbit. But as you go through that resonance, which is where this cursor is here, you can see that the reverse processing components also come into play. So we know that as that system goes through resonance, the orbit gets squashed a bit before it becomes more circular again down here. So this is visible from this, from the full spectrum Cascade plot. This time we've still got the 1x, the 2x, and the 3x frequencies plotted, but the line goes now through the forward and the reverse processing in the diagonal direction. So with Cascade plots, one of the things that we can tell, we can tell how frequencies line up relative to the speed, but we can also see vertical relationships. So in this scenario here, this is if I remember correctly, this is a startup. As the machine was running up, the 1x frequency excited some sort of a natural resonance here. I'm not sure what exactly that was, but it settled down again quickly and carried on as the machine started up. As it went through a larger resonance, this is more likely the machine's natural frequency, it excited that frequency again. And we can see now by drawing a vertical correlation line through these, we can see that those are the same frequency. This gives us a hint that there's probably some sort of a structural resonance, and it's fairly low frequency down here. So maybe a structural resonance of something that got excited during that machine startup. So this could be, this information that could be used for stiffening structures and that. Another item of note for Cascade plots is that because we're laying out the spectrums relative to speed, if you have a machine that maybe like a steam turbine where you go through a heat soak, you will see a denser collection of spectrums during that particular speed. So in this case here, we can see that the spectrums, they stack up fairly regularly, but here in this particular line, there's a denser set of spectrums. So it seems like the machine set at this particular speed, maybe just below 5,000 RPM for a little while before carrying on the startup. So this is another piece of information that you might see on a Cascade plot. So both waterfall and Cascade plots are spectrums laid out one after the other. To review, waterfall plots are relative to time, and Cascade are relative to speed. I used to have real struggles remembering which one is which until I figured out that waterfall has a T in it, so it's relative to time, and Cascade has an S in it, so remember that that's relative to speed. So hopefully a little handy mnemonic for you to remember the difference between waterfall and Cascade plots. Next, I want to review Bode plots. Bodes are a representation of static data, but in contrast to a trend plot, we're now plotting the data over speed on the x-axis. We still see the amplitude and phase, but now we're seeing it relative to speed. And there's a lot of information that can be gathered from a Bode plot. Things like slow roll vector. So in this case, we're seeing two trends or two lines on this plot here, the blue one and the red one. If we go up to our header, we can see that it's the same probe, but there's a difference between them. The blue one is just the 1x vector, and the red one is the 1x compensated. So what do we mean by compensated? So at these low speeds, before there's any real dynamic forces acting on the machine, we still saw some quote unquote vibration. And we know that that isn't really vibration because there's no dynamic forces. So we can tell now that's run out. So at those slow roll vectors, we can choose one particular value, set it as a reference, and tell the software to compensate for it, and it drops it back down here. So now at the slow roll, we're seeing no vibration until the machine actually starts to respond to the forces of the increased speed. We can tell that the slow roll vector by looking at the amplitude. So here it's roughly half of 0.5, and the phase is around 270. And if we go up to the compensated line here, there's a thing that says what our slow roll vector is. So 0.267 at 269 degrees. We can also tell our slow roll speed range. So this is the period of time where, although the speed is increasing, there's no vibration response in the system. This tells us that this is before the dynamic forces really are acting. So we can say that from 0 to roughly 1,000 would be the slow roll speed range for this particular machine. We can see the balanced resonance frequencies. We can see where that peak occurs. And in the midst of where that 180-degree phase shift happens, we know that's where our balanced resonant frequency is. And by putting the cursor on there, we can see now that the balanced resonance frequency occurs at 1,610 RPM. We can also calculate the synchronous amplification factor. I won't spend a lot of time on this, but basically you take the peak at the resonant frequency and then draw another line at 0.707 of that peak, figure out the speeds, plug them into the equation, and this gives you a numerical value that represents the synchronous amplification factor. And really what that tells you is how steep or how sharp the machine reacts to going through that resonance. If you have a lower SAF, it would be a more sort of a dull peak here. And if you have a higher SAF, it's a much sharper, taller peak. That all depends on damping and other characteristics of the machine. Heavy spot location, it's a little bit tougher to visualize with the Bode plot, but we'll show you how to see that in the polar plot. And the rotor mode shape. In this case here, we see one very clear first resonance and then no response in the system beyond that. So we can be fairly sure that we're still in the first mode shape. And if we start to see another response here and another phase shift, we can determine that we're likely going into the second mode shape. So that is the Bode plot. That's amplitude and phase in two Cartesian plot formats, one on top of the other. Now, if we take a look at a polar plot, it's basically the same information as the Bode plot, but now we're combining it all into a single plot. So we've got our amplitude still. In this case, the amplitude is demonstrated or visualized going from the center outwards. We can also see the scale on the right-hand side here. And next, we see the phase. The phase is represented from 0 through 90, 180, 270, and 360. And the 0 point lines up with where the sensor that we're showing is. In this case, we can see from the header that the sensor is located at 45 degrees right. So that's our 0 point, and then it goes around from there. The phase goes around from there. And speed, instead of being an x-axis like it is in the Bode plots, speed is now marked by labels on the actual plot samples themselves. So what information can we get from a Bode plot, a polar plot? Well, we can still get the slow roll vector. In this case, this plot has already been compensated, and our slow roll vector is noted up here. If it were uncompensated, the shape of the Bode plot would be the same. It would just be offset from the center, from that origin a little bit. But in this case, we've got the slow roll. The balanced resonance frequencies, again, we can gather that. You can see the highest, you pick the highest amplitude point, and you put your cursor there. And here we can see where that cursor is. It's 1,934 RPM in this case. We can also calculate the SAF. In this case, instead of 0.707, we take a line and do 45 degrees left and right. Find the speed at each of those points and plug them in. And this again tells us how the system responds to going through the resonance. And with a polar plot, I really like using the polar plot for visualizing where the heavy spot is. So remember in the Bode plot, we could very nicely see where that slow roll speed range was. That's where the amplitude and phase doesn't really change. In a polar plot, that just means that it's a single dot here. So there's nothing really to see for the slow roll speed range. But once the system starts to respond to those dynamic forces, the amplitude and phase start to come out. So if you go through the MDS course, you'll know that there's kind of three characteristics to figuring out where the heavy spot is. Well below the resonance, the response is roughly in the direction of the heavy spot. So here, well below, we know that this gives us a clue that it's out here somewhere. At resonance is 90 degrees from the heavy spot. So if we take our resonance and we go 90 degrees, it shows us that it's up here. And well above resonance, the response is 180 degrees from the heavy spot. So if we go well above resonance, it's out here, to 180 degrees. Again, all three point to roughly this area where a heavy spot is. So if I were on site and I was asked to balance this machine, I'd likely start putting balance weights in around the 110 degree area of that particular shaft. And rotor mode shape, again, you can see it here. This is just one big loop, and it seems to kind of be stuck there. If you were to see another loop starting, either in one direction or another, that might give you a clue that you're entering the second mode shape. But in this case, we can be fairly certain that we are still in that first mode shape. I want to jump back quickly to one steady state plot format. In this case, it's amplitude and phase versus time. This is sometimes mistaken for the Bode plot because it does have the amplitude and the phase laid out one on top of the other. But the important differentiation here is that it is over time. So this is more of a trend plot representing 1x amplitude and phase. If you do see during steady state, we can also represent the same data on a polar plot. And generally, if you're looking at steady state data on a polar plot, under good conditions, it should just look like a dot. If you do see movement during steady state, so in this case, you can see that there are the RPM labels here are the same. So the machine is running at a constant speed, but the amplitude and phase is changing drastically. As you can see here, it's also changing drastically. This is an indication that some other condition in that machine is shifting. That's a note for concern, and that should definitely be followed up on. But I wanted to highlight here that polar plots, particularly less so in kind of day-to-day condition monitoring, but more in diagnostic occasions, polar plots still can be very useful during steady state conditions. And the last type of plot format I wanted to look at is the average shaft centerline plot. So whereas the orbit plot is the instantaneous position of that shaft centerline, the centerline of the shaft, the average shaft centerline shows the average position. So if you were to kind of, again, put that imaginary pencil in the center of that shaft, and you were to then take that shaft and roll it around through the clearance inside the bearing, that pencil would basically draw this line here. So this is the bearing clearance marked on the plot. And then using the XY probes, and instead of using the AC component of that vibration signal, which gives you the vibration and then the orbit, we now use the DC component of the prox probe, and that gives us the average position. So if we were to look at this information during a startup or shutdown, it would look something like this. So you'd see that machine, you'd see that during a startup, it would start at the bottom of the bearing because gravity basically has it sit at the bottom. But as that shaft starts rotating and starts rising up on its oil film, on that oil wedge, it's going to rise up within that clearance of the bearing. So during startup and shutdown conditions, the shaft centerline plot can be useful sometimes. At steady state conditions, the shaft centerline plot also tells you something. Again, as with the polar plot shown before, if all things are going properly, the shaft centerline plot should be basically a cluster of dots in one area. If you start to see this drifting, or you start to see it shifting back and forth somewhere, or up and down, that tells you that there's some condition in that machine where a preload or a load is being let go or changing, or conditions are something shifting in that machine. Steady state conditions, the shaft centerline plot can be a useful bit of correlating information. And finally, you'll note up top here that I've got both steady state and or static and dynamic data indicated here. And that's to show that by overlaying the instantaneous shaft position, which is the orbit, on the average shaft position, it kind of gives you the complete picture, the complete picture of where this shaft is within that bearing clearance. In this case here, we've got plenty of space, but if we were to move this closer to the edge, the shaft centerline alone might look like you've still got some space, but if you overlay the orbit, it might show you that you're making contact with the bearing clearance. So some useful information there, hopefully. I'd like to thank you all for joining and participating here. Again, this webinar was a nice summary of the what of the different plot formats. If you're interested in learning more about the why, I definitely encourage you to check out the Machinery Diagnostics course. And I believe we've got some questions to answer now, John.
That's right. Let me stop the recording and thank you, everyone, for your attention.